First of all, thank you very much for inviting me today. I'll be talking about some of the projects we have. And let me go to the introduction. Here you will see Meryl on the top image, and the second image is we are under the permafrost tunnels. So my talk also will be two separate parts. The first part, I'll be talking about what is going on right now in NASA and some of the things with the standardization of the machine learning and AI. And after this, slowly, I will move into the water extent problem, which many of you probably touch this way or that way. And at the end of this talk, hopefully I will convince you that there's a very nice relation between the social networks and the river networks. Having said that, this is not a finished study, still continues. I do expect that in 2 to 3 months will be done. So you will not see any final conclusion, but you will get the idea, hopefully. First of all, I would like to show you this flowchart. We have been going through some of the proposals submitted to NASA. As you can see, there are many more machine learning and AI applications began to get into the many proposals from Musk's RCNN to random forest to recurrent networks to many other type of machine learning algorithms, and getting more and more actually. In the future, technology group also focusing in different sides of the machine learning and artificial intelligence. For example, I have a heavy interest to quantum computing and machine learning together, but those are some of the different pieces of the focus areas for NASA. And before getting into the digital transformation, so I have a different heads, I will call it. One of them is I work for the NASA. I'm the part of the Biospheric Sciences Laboratory, as well as a member of the disaster group in headquarters. So all these images I'm showing basically this way or that way coming from these departments. Currently, digital transformation is a very important part of NASA. Many things are changing. And purposely, I put this one here, as you can see on this triangle, right, from zero trust architectures to mixed reality to intelligent automation is part of this transformation. Each of these slides, by the way, requires at least 20 to 30 minute talk. So I'm just touching them so that everyone informed this is happening out there. This means many things will change. Another important thing is right now is happening in NASA. Most of the proposal calls began to change. Before, maybe we were talking about only floods, maybe wildfires and so on. But now we are talking about the cascading effects, right? So any machine learning algorithm or artificial intelligence problem has to adapt itself to this new structure. So that means the architectures probably needs to be adapted to the new realities. And the recent disaster call actually was one of the examples for that. The second, out of NASA, I also involved with especially the AI machine learning standardization problem. As you can imagine, this is a major issue, and needs to be very carefully studied. I specifically focus on the data-related applications, how the data will take a shape, what will be the approach to the metafiles, what kind of information we need to give to the scientists, right, when they are applying the data sets. So this is one of our report, which talks a lot about the best practices and similar ideas. I have to emphasize that I look at your talks actually, and I see that you have lots of different examples, and I strongly believe that each a talk actually in your group is one use case almost, and to putting them into a semi-structural format will be extremely valuable work. That's why I think the book is very important, which you mentioned earlier, and but maybe in graph ML format or something similar to, so that we can study, apply machine learning algorithms on that specific cases. The biggest challenge for the machine learning and why we are using basically the data is getting more and more. And if you see on my first slide, we have a lot of information, but it's not turning into the knowledge. So those are some of the new technologies that is coming very near, mid, far. This is from one of Applied Physics Laboratory study. I think it's a beautiful. It has the reference, and we expect that data will be much more than today. And we are talking about the digital twins and all that 7 billion of Internet of Things. So the things, the data sets are growing. And as I mentioned, AI and machine learning, that's why it's very popular these days, right? Rapid response to because of the AI speed and many other ways which can capture all these different patterns at the same time. One very interesting thing, you can put the discrete data with the continuous data in the same place, like the flags, and combined with the AOD data, for example, and still machine learning will work. And the final thing I really would like to emphasize, we need to understand the limitations for the AI and machine learning. When we use data, which I mentioned earlier about the meta files, we need to push how this data is established, right? Who are the groups, for example, labeled the data? Can we have some type of a human bias, right? I mean, we always talk this kind of information. Those has to be pushed to the scientists, so that when we take the data and try to apply the UNet algorithm, right, we have to know what are the things behind these data sets. And that's why we call it meta sheets instead of meta files. Multiple information has to gather together. So now this was the first part of that nice image. Now slowly we will go to the underground, meaning that in order to put together all these best practices and the applications, we need to understand what is going on behind the scenes, how we are modeling developing the system, how deployment happens, and the operational. So rest of the talk will focus on the development part mostly. And this flow, by the way, is not complete. I'm still working on it. And one of the things I would like to do, what kind of new jobs is coming on the way? And so, as you can see, I will try to put together some of the new, like where the data engineers comes, and the development of operations, machine learning operations, all these flows, what kind of information levels we need. So let's continue. So now, probably many of you are familiar with the HydroSAR project. And so this is one of the use cases to all the things we talked earlier. But I involved with this project as a co-I. And I basically implement some of the machine learning algorithms to get to do that water extent maps. So currently, actually, this product is a very nice product. It's already implemented. And you can go ahead and basically download the data sets where with the water extent maps on them. And these things are all created using the SAR data, which is a very powerful instrument, right? It can see through the clouds and so on. The idea in the current implementation is basically a automatic threshold calculation. There are lots of very important steps in this. I strongly suggest to look at every piece, how it is working, because it's not that trivial, all these calculations. We have the SAR image stack and the digital elevation maps. From there, we pull all this information and the flow. At the end, we end up with the flood maps. And so after HydroSAR project completed, the next thing happened was the HydroSAR's next generation. So in the next generation, the idea was, at least on my side, the project is much bigger. It includes the landslides as well as the extent, water extent, how the machine learning algorithm can come into the picture and improve the results. So basically, general idea here, I will go to the next slide, include the GeoGlobe forecast river flows, combine this information with the HydroSAR data, and they apply some type of a machine learning algorithm. As you can see here, there are two of them, which I am concentrating in the second part, LSTM. This is long short-term memory network. Later on, I will show that, by the way, there are probably better models to do this problem. And so at the end, our goal is to be able to simulate the water extent maps. That means there are two things here, right? One of them, data comes, we turn them into the simulated data, maybe use UNet or something like that, but also put into a quant what is happening temporally to the river flows. And you will see soon that how important that is, especially for the HKH area. So I just put this one. This is one of the example to HydroSAR, actually. On the left is the pixel corrected image coming from SAR, meaning that all the nuns and these and that removed. And the right-hand side, what the HydroSAR gives. So as you see now, I updated the LSTM to convolutional LSTM. The LSTM by itself actually only considers the temporal data. But if we look at our images, right, there's a spatial correlations as well in them. So LSTM by itself will not work, and we need to go one step forward. So this is the updated basically flow. Now, the problem is a little bit more difficult than what it looks like here. The reason for that, RTC, this is radiometrically trained corrected data sets, are images, comes every 6 or 12 days. Depend on how many data we are considering, but GeoGlobe data created using every day. So there's a data frequency problem needs to be resolved. And right away, without getting any detail, there are two approaches we might do here. One of them is that we take every 12 days and get the corresponding GeoGlobe data. We create the sequences and apply the convolutional LSTM. But we are losing a lot of information for this case. For the second one, we collect the daily GeoGlobe data, apply separately convolutional LSTM, get some predicted GeoGlobe anomalies. By the way, GeoGlobe data has also forecasting data in it, but this way I strongly believe is much more powerful. And after that, maybe use some type of a generative UNet algorithm, and at the end, obtain the synthetic SAR images. So this is like two approaches, but what's going to happen when we study these things, our flows will improve, right? We will find some other features in data sets. which will affect the overall architecture. So this is just the two examples that we can consider. So I will go back to the LSTM, choice of convolutional LSTM, CNN algorithms, and all that stuff. We have to be considering very carefully what are the spatial components and what are the temporal components, which actually creating this image we have on the left. And from there, we have to move to the segment water bodies and probably do some predictions on them. So let's look at the GeoGlow data a little bit. As all of us know, river flow is a spatial temporal problem, right? Conditions in one place affects the other side. Rains on the north, if the river going through the south, right, we began to see in 1 or 2 days with a time lag increase in the water amount, how much water is going through. The patterns is dynamically changing very heavily, right? And very quickly at the time. So how we gonna consider including the weather conditions? Also, whatever the architecture we're gonna put here has to handle the very big data calculations as well, right? So that all these networks will be handled properly. Now, I'm going to show you actually numbers only for Nepal very soon. You will see how big these systems actually, if you consider fully. So, considering the all these methods, as you see, I included convolutional LSTM, which is a spatio-temporal can handle, but works on the gridded data. That means if I have a map, right, I would like to have the grids and all that features on the image. And certainly this is an easier way to solve the problem. It will work, but it has its own problems. And the second one, we start to study actually about a month ago or so, graph wavenets. What we observe is that gridded data might be nice, but the river is not acting as a gridded data. So they are basically irregular spatial structures, right? We have to understand when it's rain on the north, what's going to happen in the south. And they move along the river path. So it's not like the whole image, but each river has its own characteristics. And so the question came how we can represent these graphs in a graph form, such as rivers in the nodes and edges. And the convolutional LSTM can go quite big. It depends on how much historical data we will take. Maybe graph wavenet will help us on that because now we're going to go to the nodes and the edges instead of the whole X by Y image. And finally, after studying this method, we find out that it can capture quite complex relations. So in one system, you can have multiple networks, and the method actually will try to find the correlations between these multiple networks and even create new adjacency connections, adjacency matrix connections. So it's a very interesting method. So when we apply these problems, we follow a very classical order, right? We have the raw data. If we need to index the data with the dates and so on, we do that. We do a cleaning of the data. Like if there are unacceptable outliers, right? We remove them, annotate if it's needed, which is labeling in this case. Also, we try to validate the data itself so that the training data sets are useful for us. That includes the biases and all that things. And the rest, everybody knows, splitting, training, testing versions, and so on. So how we prepare the GeoGloves data. Now, every river is different, right? There's a small one, there's a big one, there are streams. So how are we going to bring them into the same dimension? Let's call it that way. So the first thing we do is GeoGloves. I'm learning this data set, by the way. You have to do a lot of preliminary calculations and analysis. One of them is that I like to use the OpenStreetMap for some problems, right? Because there are the buildings and this and that. But I need, they have different IDs, unique IDs. So we need to kind of understand that structure. We can collect what is called reach ID in GeoGloves and basically collocate them with OpenStreet IDs. After that, now we are in a better shape because we know exactly mapping from one to other. And I have all the polygons from the OpenStreetMap. Basically, I can match the GeoGlove flows to the OpenStreetMaps, which is in this case rivers. So now what happened that I basically enriched the OpenStreetMap with how much metric cube second water is going through. And in order to detect the anomalies in the whole picture, right, we look at the simplest method in this case, calculate the z-scores, which is a formula right here, and try to understand what is going on. Now, HKH region is a very interesting region, right? The rain starts very specific times, and if you are in the April, June times, there's no any rain. So we also focus sometimes season to season or month to month. Let's say all the data collected from 1972 and to now, and try to see how the normal behavior for the specific months. And we choose 14-day signatures. This might be different numbers, which we didn't analyze. What is the optimum case? Something to look into in the future, probably. So it's very, how we say, general view of the some of the riverbeds. Every dot comes to a little bit complicated, how we say, multiple rivers is getting into. So on the right-hand side is a little bit more focused. If you go to the dots over here, most of the time, there's a more complicated structure under it. So this is kind of showing what this river flows looks like in metric cube second. As you see, it's lots of different shapes, and they depend on the shape, how much water going through. However, once we apply the z-scores and we began to see these anomalies in daily GeoGlove flows. If you look at the day one, for example, there is something small here happening. And if you go and you can see much better what kind of rain events maybe it's happening at that time. And so the water amounts are much higher. So this means anomaly means here water levels is much more than expected at that time. And you can see just general daily how this is changing. So I just put one example here on the left side, no anomaly case. This is exactly the same day on the right-hand side with the image. And now I'm going to show you. I hope you will be able to see the difference. Now, on the left, one image with the anomalies. I'm going back and forward. As you can see in the middle here, water bodies is classified as a little more, much more than the other times. So this is actually a very nice signature for us to go on it, right, for the modeling of the problem. So basically, currently what we are doing is that we have the GeoGloves data is coming in, Sentinel-1 data, in this case SAR, coming in different frequencies, and we have the water masks, which is actually created by the HydroStar images. We have the separate product for that. So I mean, the simple idea is the first thing you think about, okay, we can use this mask as the labels, which is very nice, and they train and try to do the forecasting at the end. Now, we have a little bit more goals here, right? We want to take the GeoGlobe and match with that mask. That is one of the things we would like to do. And they are on the top, apply the convolutional LSTM if we can. And from the red to blue, probably use the UNet and see if we can estimate if we can get the images correctly. And the first thing we're going to consider is the UNet part. Are we going to be able to even work that? And as a matter of fact, it works very good. And this is one example here. One of the image might be 7,000 by 9,000 approximately in image. We created 256 by 256 patches, and we did additional data creation steps, which I'm not getting into the detail here. And they split the data 75%, 25%, reorganize the data directories, and all that things we went through. And this is the example of the directory structure. And the system worked. So now what I will do, I will give you a small example how it is, what the mask looks like, in this case label, and what the image is on the left side. So this is one of the patch. So basically we create all the data sets like that. And this is the example of the intersection of unions in the estimated areas and the loss functions, validation loss and training loss. It works fine. And don't forget, this is just a subset of the data sets. So we didn't do the full training, but we have 3 years of data. I think this is about a year or so. And those are some of the results. And if you look at the left, this is the testing image. On the middle, we have the label coming from the hydrosar data. And if you compare the testing image to the label image, looks like we are losing quite a bit of information right here. And the river is not fully available to us. And on the right-hand side, once the prediction happens, actually, somehow we recover some of the information. That was something interesting. So the second example at the bottom, this is another patch, and the similar behavior actually is happening. So then the question comes, why this is happening, right? And even though testing labels, losing some information, there is something missing. So we need to do a little bit more digging into that. So those are some additional trial we did with different epochs, with different inputs. We did a lot of trials on that. Now, going back to our water mask from the original hydrosar, we thought that we need to look into how the thresholding is happening, why we are losing so much information. Maybe not so much, but it's not as we want to see. So then we get into the details. So this is the life of the machine learning person or learning algorithm person who applied the data preliminary analysis. We began to look into the details. For example, the first one is the original. The second one, water mask, something called fuzzy approach, where some of the outliers are removed in the original hydrosar and the final initial estimation. So basically we studied this and we find out the following. Let's take, this is the original image. And the left side is the hydrosar water mask, which is quite good. On the right side, we did very similar thresholding, but this time we didn't use the fuzzy logic or anything like that. Basically, manually we adjusted the image. So we have almost the same rivers, right? But lots of noise is happening around it. And this is the showing the noise and all together. But there are also many more streams can be seen here. And to be able to capture that lost information, especially for the labeling, I need to use a correct semi. That is this, not AE. We use a tool we created earlier, which we use for the multispectral data sets. Basically, what we do, we give the subset much smaller area where the water signatures are. And from that, using some random forest near neighborhood searches and try to build the labels. So there it is. This is the right-hand side is the built label. This is an example from the Turkey Edirne floods, actually. And we can do this, by the way, multiple satellites, including Planet Data, Landsat 8, Sentinel-2. So we apply exactly the same thing to the severe data, successfully, I will call. And one of the power of this method is that the results are not zeros and ones. Instead, they are probabilities. So we updated the actually random forest algorithm to the probabilistic outputs. And very successfully, we got that. And currently, we use these labels instead of the original mask created by the hydrosar. Basically, I call it augmented labels, which uses the hydrosar outputs and creates this. Now, so this is all spatial side of the problem. The other side, very quickly, I will go 4 more slides and I will stop there. This is the very general from the GeoGloves website. I captured this image. As you can see, the big river beds, right? And if you concentrate only on the Nepal area, I will just, and if you retrieve the rivers, actually, this is what you see. Now, we have to be very careful here to include all these details. And all these small rivers, actually, all the flood extent maps, floods needs to be captured in the model. And I just take the subset of that. And here you can see 63,734 stream patches. Patches means they are not rivers, the whole rivers, but the pieces of water flows that creates that rivers. And if you go down to this new lower, the more focused one, 468 patches right here on the right-hand side. Now, so we are moving towards the graph wave net, right? And this is how we are doing. The most difficult thing to do with the graph wave net is to establish the data sets, put them into the new format. So this is what exactly happens here. And as a matter of fact, if you take this subset, we were able to actually build the network here. And when the rains more and more happens, let's say big rain events, these networks changes actually, meaning that the new river flows includes. And currently we can handle that these newly created streams if there's a data about them. So this is very hopeful. And in this image, actually, once the network is established, we can exactly define 44 rivers available with all that little patches. Now, this is my last image, and I call it linked data sets. And extremely important to build these linked data sets for the purpose of the explainability of the system we're going to create. we'd like to know every piece of information contributing to the floods, and we would like to know how they are changing. And also, we would like to have the flexibility of not only measuring the river flow, but for each node, we would like to know if there's a rain. So this system will allow us to go to the next level, we strongly believe. Now, we did the currently UNet implementation. We complete that. Certainly, we are continuing to work with the river networks, but we are done with the data handling part, which was the most difficult part of this problem. We mapped the unique IDs from OSM to GeoGlobe, so we can basically go back and forward without any problems and very quickly. And lastly, we already run very simple cases which worked fine in the graph wavenets. Now, I will leave this subject to probably another talk, and I will just stop here. Thank you very much for listening, and if you have any question, please let me know.
That was wonderful. That was so great. Thank you so much. Let me go right into, I think we saw a couple hands up. Ollie, did you raise your hand? Go over to you. Oh, there we go. Over to Meryl.
If no one else, I have lots of questions. Could you go back and explain a little bit more about what the challenge was? Like originally HydroSAR was a binary mask, and you mentioned you had to redo the way it represented data. You had to include in certain pixels. Could you review that again or explain again why, what the issue, how you ended up fixing it? Like if you ended up using, there's so much information I couldn't get it all.
Yeah, I know it's a complicated process. First of all, I don't know if you are talking about convolutional LSTM to moving towards the graph wavenets. Is that the question?
It was. I think you said you ended up using random forest. It was so.
I see. You
encountered the issue where you lost information in the original one, and you had to.
Let me go back to the. So you are.
And you had to look back at the HydroSAR algorithm to understand why the training was losing information and gaining it again. Yeah. So when like the fuzzy logic process, could you go over this again?
The truth is that this is a very well, implemented method so I came this project, by the way, halfway, right? So I was kind of independent eye to look at some of the pieces already introduced. And I really like the idea of, for example, after the general thresholding, using the fuzzy idea, which is by itself, whole subject. But what happens is that when we talk about the disasters, right, we have to be conservative, meaning that sometimes might be underestimating up to some level might be a better thing than overestimating. So this is all depend on how you approach the subject. Certainly, I'm not saying this has to be this way. So my understanding was the current HydroSAR algorithm was underestimating some of the pieces, and this is not a bad thing. Actually, it's a good thing. But so it's not creating false feelings, right? There's a over extent of flood while they are not there. So, but for my purpose, I said I can use that in a positive way, right? So underestimating, let me go to another image here. So these two images, right? The left side, get the rivers, fine, is perfect. Some of the streams, fine. Now, if you look at these small ones, right, we are losing a little bit information there. And so I said, okay, let's do the thresholding with just, I would say, poor man's method. Just go there and adjust the numbers, look at the distribution of the data and so on. So the right image is up here. And I said, okay, so this is what we can do. Let's take the left one, use these masks, right? Apply to the original image, whatever that mask is, and use that selected mask points as a starting point and began to check all the corresponding, neighborhood pixels if they are correlated with this mask. So that is the basic question I ask. So once there's a correlation, I was able to expand to the points weren't included in the original hydrosar. Now, when you apply forest the algorithm this way, what happens is that it's like you are using multiple thresholds, right? Let's say there's a shade on one side of the image, there's no shade on the other side, which is not the case for SAR, but that is how it works.
You're correlating between the water mask and then optical image?
No. This is just an example to show you how this method works. We never use optical image. This is just, I had a flow chart, that's why I put it here. But the idea very same what I'm doing right now. I should have been more clear on that.
So sorry, you can keep going. So, okay, so you correlated between the mask and the original SAR image?
Yeah, mask coming from the original SAR image, right?
Okay.
So now we are rerunning this using the random forest, using this mask as a starting point, and basically rebuilding the probabilities for that similar pixels. If it's not clear, certainly, how you say, after this meeting or something, sometime we can get together and I can create a better flows for you.
Okay, I appreciate that.
I'll be more than happy to do that.
If anyone else has another question, feel free to go for it. I can take those.
Sure. Thank you, by the way.
Yeah, I feel like first off, fantastic presentation, and also like it shows how much we could have given you about 4 hours, to be honest, because there's so much here, and you only really touched really on sort of the cutting edge of the next generation of this. So there's so much that was in the history too that you condensed down. So really excited that of this presentation, and I think as you're advancing with the collaboration with Franz in the life of this AST, the door is always open for more presentations if you're ever interested. And I think you brought up the good point with the discussion with Meryl. If there's a space or time to collaborate through the discussion, we have the Google Groups, which is a great place to chat about some of the methods as well. And that way it's open for other folks who join the group to sort of see a little bit more about the technical work and how these methods all sort of apply. So these are great landing points for people to sort of come back to these different methods. So again, I just want to thank you. A really fantastic presentation. And again, if you're interested in future talks, we'll try and give you even more time.
Well, I mean, 3 months from now, I'll be more than happy to give you the final results actually for the graph wave nodes. That will be publication level, hopefully. And I was able to meet with the SERVIR group actually from Nepal and India and Bangladesh this December. And this picture is actually taken from that time. and it's an honor to work with them. So I just want to let you know that. Thank you.
Yeah, thanks so much. And I'll reach out to you about another presentation in a couple months.
Perfect.
Thanks, everyone, and we'll talk in 2 weeks.